In this video, we're going to discuss how to work with statistical tables in order to evaluate the probabilities for the normal distribution. What we want is to explain and predict a random phenomenon, and many random phenomena around us follow the normal distribution. For example, scores of students after some exam or the IQ scores of people follow the normal distribution, and it is incredibly important for us to know how to evaluate the probabilities for the normal distribution. When we say that the random variable x has the normal distribution, it means that its density curve is like this, which is given using this function. So this function depends on the two parameters, the mu and the sigma. Mu is the mean value of the random variable, and the sigma is the standard deviation of the random variable. So by changing the values of the mu and the sigma, we can change the curve, the shape of this curve. For example, if we're going to change the value for the mu, we're just going to change the position of the peak value of this curve. And by changing the sigma, we're going to change the height of this curve. So if the sigma is bigger, then this curve is going to be more flat. And if the sigma is smaller, it means that a lot of points are around the mean. It means that this curve is going to have higher height. So one of the spatial forms of the normal distribution is when the mu is equal to the 0 and the sigma is equal to the 1. This kind of curve is called the standard normal distribution when the density function simplifies a lot. So this is incredibly important to know what is the standard normal distribution, because we're going to use this in order to evaluate the probabilities for the normal distribution. So if I would like to evaluate the probability for the normal distribution, I need to find the area under the normal distribution curve between the two values of the a and b. And we can do this, for example, by integrating the density function in this region from a to the b. So you see, so the integration of this function analytically, it's unfeasible, and we can either do the numerical integration in order to evaluate the areas, or we need to figure out another smarter way to integrate or to find the areas without integration. So the idea would be like this. So if you're given the normal distribution with the mu is equal to the 1 and the sigma is equal to the 2, if I would like to find the area between a is equal to the 0 and b is equal to the 2, I would find the area which corresponds to this area under the standard normal distribution curve and evaluate that area. So basically, I would like to find the area under the standard normal distribution curve, which is going to be the same as this one. And by evaluating this, I can find the area under the normal distribution curve. In order to find what exactly area I need to find under the standard normal distribution curve, I need to find the corresponding points for the standard normal distribution curve, which correspond to these 2 points, right? So this point z is called the standard square of this point x, and it is calculated by subtracting the mean from this x and dividing this to the sigma. For example, if I would like to find the z1, which corresponds to the x1, I'm going to subtract the value of the x1 minus the mean of this distribution divided to the sigma. It's going to be minus 0.5. This is going to be the standard square of this x. So in order to calculate the standard square of the xt, I'm going to subtract the mean from this value and divide this to the sigma of this distribution, and it is going to be 0.5. This is going to be the standard square of the xt. So the area under the standard normal distribution curve between minus 0.5 until 0.5 is going to be the same as the area under the normal distribution curve between 0 and 2. So the general idea of calculating the areas under the normal distribution curve would be to find the standard scores of the points and evaluate this area under the standard normal distribution curve. And now we need to discuss how to find the areas for the standard normal distribution curves. So in order to do this, we're going to define the function phi, which is going to give us the cumulative area until some point z. So basically, phi of z is the area under a standard normal distribution curve until some point z. So for example, if I would like to find the area until, so in order to evaluate the values of the phi, we're going to use the table which is called the z table or the standard normal distribution table. So this table gives us the values of this function phi for many values of the z. So the first column and the first row is used for the values of the z, and all the values inside this table are the values of the phi, or the areas, right? So if I would like to find the area under the standard normal distribution curve until z is equal to the 0, I need to find a 0 from the first column and 0 from the first row. And the area or the value of the phi at the 0, it's going to be the intersection, 0.5. Or for example, if I would like to find the value of the phi at the 0.94, I'm going to find 0.9 from the first column. Then I need to find 0.04 from the first row because their sum is going to give me 0.94, right? And the intersection of these 2 points are going to give me the value of the phi, which means that the area until 0.94 is equal to the 0.82 roughly. So now we know how to evaluate the areas until some points under the standard normal distribution curve, and we're going to use this in order to find the areas between 2 points. So if I would like to evaluate the area between the 2 points z1 and z2, I would find first of all the area until z2 using the table. Then I would subtract from this the area until z1. This would give me the area between z1 and z2, right? So you see, so in order to calculate the areas, I need to know how to evaluate the values for the phi, for negative values of the z, and sometimes for the positive values of the z. So usually the table of the standard z table is given for the positive values of the z, and we need to learn how to use the table which is given only for the positive values of the z in order to evaluate the areas for the negative values of the z as well. So since this curve is symmetric, it is just enough for us to have the values for the z, values for the phi, for the positive values of the z. So here, if I would like to find the area until some point minus z, this is going to be the same as the area until the positive value, after the positive value of the z. So this area on the left tail is going to be the same as this value on the right tail. So if I would like to find this area, what I can do is I can find the area until this point by evaluating the phi of z. And by subtracting this from the 1, I can find the value on the right tail. And this area is going to be the same as the area until minus z. So let's consider an example. So if I would like to find the area until minus 0.92, I'm going to find the value of the phi of 0.92, right? So in order to do this, I will go to the table. I will find 0.9 from the first column, and then I need to go to the first row and I need to find a 0.02 because their sum is going to give me 0.92, and the intersection is going to give me the area until 0.92. So the area after 0.92, it's going to be 1 minus the area of the until the 0.92. This is going to be 0.17, and this is the same as the area until minus 0.92. So now, if I would like to find the area between minus 0.92 and plus 0.92, I need to find the area until 0.92, then I need to find the area until minus 0.92, then I need to subtract them. So the area until 0.92 is equal to the 0.82, and the area until minus 0.92 is equal to the 0.17, and the area between the 0.92 and minus 0.92 is going to be 0.64. So sometimes it is important for us to know what are the z-scores if we are given the areas, right? So in statistics, there is if you're given the confidence level or the significance level, it is important for us to know the test statistic or the z values here. So the confidence level is the area in the middle in the middle of this under this curve, and the significance level is the area in one of the tails or in both of the tails. So for example, if we know that the area in the middle is going to be 0.8, how to find this z-score or this z-score, right? So we know that if the area in the middle is 0.8, then the areas on the tails is going to be 0.1. Since the total area under this curve should be equal to the 1. So this is going to be 0.1 here, 0.8 here, and 0.1 here. So if I would like to find the value of the minus z or z, which gives me, so that the area between minus z and z is going to be 0.8, I need to find the value of the z, so that the area until this minus z is going to be 0.1, right? So phi of z, or I need to find the value of the z, so that the area until this value of the z, it's going to be 0.9. So in order to find this value of the z, I'm going to go to the table again. So from this table, instead of, so previously we found the value of the z, then we found the areas. So now we're given the area and we need to find the value for the z. So from this table, I'm going to find the closest value to the 0.9. So this is going to be this value. And for this value, I'm going to find the value for the z. So value for the z is going to be 1.2 and 0.08. So it means that the value of the z, which corresponds to this area, is going to be 1.28. So the value for the minus z is minus 1.28, and the value for the z is plus 1.28, and the area between minus 1.28 and plus 1.28 is going to give me the area, which is going to be 0.8.